Okay, section 4.6 is applied optimization. These are optimization problems. They're word problems. These are the steps you want to refer back to whenever you're solving these problems. Please make sure you read the problem carefully. Draw a picture, introduce your variables, write an equation, test critical points. In these, we're going to have what's called primary and secondary equations. This author doesn't present the information this way, but I do, because I think it makes life easier. The primary equation, when you solve these problems, is the equation that you want to optimize, either minimize or maximize. Optimize just simply means maximize or minimize. The secondary equation is an equation that is used to write the primary equation in terms of only one variable. These are not the related rate problems where we take the derivative with respect to time. Once we have a primary equation, what we're going to do is we're going to find out where maximums and minimums, whenever a function has a maximum or a minimum, the derivative is equal to what at that point? 0. So what we do is we find our primary equation, write it only in terms of one variable, take the derivative, set it equal to 0, and that tells us where our maximum and minimum values occur. So we're going to go through this process for a couple of problems here. Example 1, find the dimensions of an open rectangular box of maximum volume. So that tells you what your primary equation is going to be. We want to maximize the volume. That can be made from a sheet of cardboard that is 11 inches by 7 inches. That's the size of the cardboard. That's going to be our secondary equation. By cutting congruent squares from the corners and folding up the sides. Then find the volume. So what we have here is we have a sheet of cardboard, rectangular in shape, that's 11 by 7 inches, right? So this is going to be 11 inches from here to here by 7 inches. That's from here to here. And we're going to cut corners out. So we cut square corners. I don't know what exactly the size is, but we cut along the dotted lines here and fold up the sides. We don't know this distance right here, but it's measured in inches. We cut along the dotted line and fold along the solid line, and we end up with a shape that's a rectangular prism, yes, of an open top box, right? They don't make us take art, by the way. So, the length of this box is going to be what? Well, we started out with an 11-inch sheet of cardboard, but I took out 2 measures of x, right? 11 minus 2x from here to here. What is the width going to be? From here to here. What is the height going to be? Okay. So our primary equation here is going to be the volume. We don't really have a secondary equation this time. By the way, we do have a domain for our variable. What is the domain for x? X has to be between 0 and what? Realistically speaking, 3.5, because this is 7 inches. And if I cut out 3.5 inches here and 3.5 inches here square, I just have a line, right? Or a flat piece of paper that I fold up with no volume. So it has to be greater than 0 but less than 3.5. Okay? So our equation that we're going to maximize here is going to be the volume. Our primary equation is volume. Volume is equal to length times width times height. Here's our secondary equations are going to be the sides here in terms of x. So our volume is going to be the length, which is 11 minus 2x, times the width, which is 7 minus 2x, times the height, which is x. So our secondary equations are just the sides for the length, the width, the height. X. Now, I said I want to optimize this. By the way, let's rewrite this so that when we take the derivative, it's going to be easier. We have volume is equal to, if we FOIL this out, that's going to be 77x minus 36x squared plus 4x cubed. FOILing that out and distributing the x. It is. I did it in advance. I'm not that quick. All right, so we want to maximize. That means we need to take the derivative. So when I take the derivative here, I get 77 minus 72x plus 12x squared. Now, I could set the derivative equal to 0, and that's what I want to do. Now, set or solve v prime equals 0. Okay? So what I have is this equation, 12x squared minus 72x plus 77 equals 0. It's a quadratic equation. I don't think this one factors, and I don't see any common factors. But I know that every quadratic equation can be solved, but I don't see how to do it right away. So what do I need to do? Quadratic formula. What is A equal to? What is B equal to? What is C equal to? And the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I expect that you know this. That's fine too. So when you do this, we end up with x equals, okay, plug in numbers. And then you end up with x equals, from the plus the square root, you get 4.6. And you get 1.4. Do we get to keep both of these? No. Not the 4.6. Why not the 4.6? It's outside of our domain, so we toss this one out. Okay? And we were asked to find the dimensions, right? So our final answer is going to be the dimensions. We now know x. This is the value that maximizes the volume. So we were asked to find the dimensions. Guess what? We go back up to here where we have the length and width, the height, and the terms of x. By the way, 1.4 is rounded. It did not come out exactly. I rounded to the nearest tenth of an inch. So this is going to be, the length is going to be 8.2 inches by 4.2 inches by 1.4 inches. And then the maximum volume is what? 48.2, I believe, cubic inches. Very good. Example 2. Moving right along. What are the dimensions of the lightest open-top right circular cylindrical can that will hold a volume of 729 cubic centimeters? What are the dimensions of the, okay, first of all, the light, what are we trying, what's our primary equation going to be? We want the lightest open top right circular cylindrical can. If it's going to be the lightest, no matter what material it's made of, we've got to use as little as possible, right? That's surface area. The material that you're using. So we want to minimize surface area. Here's our secondary equation. The volume, we know. So we need to know what a right circular cylinder looks like. Well, fortunately for us, we do. It looks like a can.
So which ones are secondary and which ones are primary? I'm sorry.
Primary's in red. Sorry. I'm being consistent with my color scheme. Whatever you maximize or minimize is your primary. Let me write that. Because when you take the derivative and set it equal to 0, you're finding a maximum or a minimum. And this is our secondary. All right. Whenever you have a right circular cylinder, that you need to know a couple of things. You need to know the height, and you need to know the radius. Were we told anything about the height or the radius? No. So we're going to use H and R here. But for a right circular cylinder, we do know that volume is equal to pi r squared h, right? And we know that the volume is 729, right? Okay. So we could solve this for the height by dividing both sides by pi r squared, and we get the height is equal to 729 over pi r squared, right? That's our secondary equation. Our primary equation is the surface area. Now, if I were to cut this can along the top and the bottom of the can and lay everything out flat, the surface area that I would be dealing with is a rectangle and a circle. One circle. We'll say it's like that, right? Where the radius of this circle is R, the length of this, or the width of this, is H. And what is the length from here to here? It's the circumference of the circle. And the circumference is 2 pi r. So the surface area is what we want to maximize or optimize. So we're going to say that the surface area, I'm not spelling this out. the surface area is equal to the area of the rectangle, which is length times width, plus the area of one of the circles. Remember, it was an open top can, so we only have one circle here for the base. And the area of that is pi r squared h. So far, so good? Guess what my variable is going to be in this equation? We know that h is 729 over pi r squared, right? I'm going to take this value for h, and I'm going to plug it into this equation right here and right here. Oh, why is there a h there? I don't need that. The area of a circle is pi r squared. No h. Sorry. That was the area of the rectangle. This is the area of the circle. I had a brain fart. I'm hungry. Low blood sugar. You too. I'm sorry. So we end up with an equation now in terms of only one variable. The surface area is 2 pi r, I'm going to put that over 1, times 729 over pi r squared plus pi r squared. Things are going to cancel nicely now, right? Pi's are gone. This radius cancels with one of these. So I have the equation, surface area is equal to, what's 2 times 729? 1458? So this is 1458 r to the negative 1 plus pi r squared. And I want to optimize this, which means I need to do what? Take the derivative. So now we take the derivative and set it equal to 0. Okay, we're going to find the value of r that does this. So, the derivative of the surface area, and I'm just going to call it SA prime. Are y'all okay with that? Mm-hmm. Thank you. It's the derivative of the surface area. I just have SA like one variable. Is equal to negative 1458 r to the negative 2 plus 2 pi r. Right? Because you subtract 1 from the exponent. I'm just using the power rule, right? Nothing fancy or tricky. The numbers are ugly, but we're smart. We don't worry about that, right? Now that I have the derivative, I set it equal to, and this is negative 1458 over r squared plus 2 pi r. Right? So I'm going to move this term over, and that's going to give me 1458 over r squared equals 2 pi r. And can I put that over 1? Because then I can cross multiply, right? Hang on, I'm just looking at my notes. What did I do? Yeah, no, I do that. Then I can cross multiply, and that gives me 2 pi r cubed. 2 pi r cubed equals 1458. So far, so good? I want to get the r by itself. That's my goal. I want to find the value of r that does what I want it to do. So now I divide both sides by 2 pi. Right? 2 pi don't bother me. Okay, so that gives me r cubed equals, what's 1458 divided by 2? 729 over pi. How do I get the r by itself? Which is just raising this to the 1/3 power, right? So I get R, my final answer, is equal to 729 over pi raised to the 1/3 power. That's R. Can I figure out H now? Sure I can. So we're going to come over here and we're going to figure out H. Okay, H we said was equal to 729 over pi R squared. Agree? Guess what we plug in place of R? There we go. Okay, I didn't like that. That looked ugly. Let's just do that. All right, so let's clean this up now because this is messy. Working with H. We now have H equals 729 over pi times 1 over R squared. But isn't R a fraction? I'm going to flip that fraction. And that gives me pi over 729. Do you see what I just did? I skipped a couple of steps. Dividing by R is like multiplying by the reciprocal of R. Y'all okay with that? Do you agree with what I did? See, I wanted to do this. And you know what? I have a feeling half of you are not comfortable with this. So this is going to be times 1 divided by 729. If you wrote down what I had and you're fine with it, leave it. But this is going to make it easier, I think. So this is equivalent to 729 over pi times the reciprocal of that, which is pi to the 1/3 over 729 to the 1/3, right?
Yeah. On the first.
2/3. 2/3. 2/3. When you raise a power to a power, you multiply. So that's pi to the 2/3 over 729 to the 2/3. Glad you said that. Now, I'm dividing with common bases, aren't I? This is 729 to the first minus 729 to the 2/3 is 729 to the 1/3. 2/3, sorry. Pi squared. 1/3, right? Yeah. All right, so this is 729 to the 1/3 over pi to the 1/3. Is that right? Oh, isn't that equal to R?
Yeah.
Isn't it?
Yeah. No.
Well, what do you know? H equals R. The height has to be equal to the radius. So, the way to get the lightest open-top right circular cylindrical can is to make the height equal to the radius. And that's it. Which is, by the way, 729 over pi raised to the 1/3 power. So it's going to be a short, fat can, kind of like that. Okay? All right, I have one more example, but I'm almost too tired to do it. Do y'all want to take a quick break? We still have time. I'm going to pause the video. I can do that. Resume. Example 3. Consider the parabolic arch whose shape may be represented by the graph y equals 169 minus x squared, where the base of the arch lies on the x-axis from negative 13 to 13. Well, guess what? This is the equation of a circle centered at 0, 0 with a radius of 13. So we can draw our little grid thingy right here. And we have our circle at 13. Let's call this 13. That does not look symmetric. Isn't it though? Okay, we're going to pretend that this is it. All right, the base of the arch lies from negative 13 to 13. Find the dimensions of the rectangular window of maximum area that can be constructed inside the arch. Well, it could be a short, skinny window, or it could be a more of a square window, but we're going to say that it's this window right here, where this is negative a and a, because we don't know. Let's not use a, let's use x's. Negative x and x inscribed inside this circle, whose graph is the secondary equation. Maximum, primary is in red, secondary is in blue. Thank you. Why don't I write it out? Primary equation, remember, is what you're going to take the derivative of. And the area of this rectangle is going to be the length, which is 2x, times the width, which we'll call y. Because this is the point y equals 169. Let me not do that in blue. Here's a point x, y. And y is the height. So we're going to use our secondary equation. Sorry. Y equals 169 minus x squared. And we're going to plug in this in place of y. So that'll give us our equation that we can then differentiate, find the maximum of 2x times 169 minus x squared. So this is 338, is that right? X minus 2x cubed. So when I take the derivative of this, we end up with a prime equals 338 minus 6x squared. Correct? Now we set it equal to 0.
And your x is from like?
Whatever that distance is, we're trying to find it. Yeah, it's how far out we go here for a rectangular window. We don't know what x is, but once we figure out what that length is right there from 0, we can go up and figure out y by plugging in. So we're trying to find x. That's a good thing to write. That's a h. So here we go. 338 minus 6x squared is equal to 0, which means that 6x squared is equal to 338. Divide both sides by 6. And we get x squared is equal to 56.33. Why don't we call that 56.3? Take the square root of both sides, and we get, you don't have to do plus or minus, by the way. We get x is equal to what? And this is measured in feet, right? Did they tell us? They didn't. All right, I'm going to assign units of feet. Because otherwise it's a teeny tiny window. This is a huge picture window. All right, so x is 7.5 feet. What were we asked to find? The dimensions, right? So then the dimensions really? My pen has quit working, really. That happened last time. The dimensions here are going to be 2 times x. Yup, this works, the pen doesn't. Yep, not working. So the dimensions, not going to be impossible though. I'm going to type. Two x, which is what, 15? By y is going to be, plug in the 7.5 for x. What's 169 minus, I think it's 113 roughly. We better do 112 3/4. Because a 1/4 of an inch can throw things really off if you're doing construction. So there's the dimensions. Find the dimensions of the rectangular window of maximum area. How would we find the maximum area of that window? How much glass do we need to buy? 15 times whatever. We got it. We're done. We made it. Lost it at the end. Wow, that's the first time that's happened in a while.